Yeah, people will join. So, hi everyone. It's a great pleasure to introduce Dr. Tamir Bendory. He's a professor at the Department of Electrical Engineering at Tel Aviv University, and he's going to talk about multi-reference alignment, representation theory perspective, sparsity, and projection-based algorithms.
Okay, thank you, Gilad. And since we are very few, feel free to stop me at any minute if you have questions. So I'll start by introducing the multi-reference alignment model and motivating this very specific perspective that I'm going to take in this talk. Then the main section is going to be theoretical analysis. It's based on the joint work with Dan Edidin. And if time permits, I'll also talk about projection-based algorithms, which is based on a joint work with Yuhao Ku, Joe Kilinis, Oscar Mikelin, and Amit Zinger. So let's first of all introduce the multi-reference alignment model. So it's an estimation problem. We want to estimate a signal or a vector f, where in each observation, f is acted upon by random group elements of some group G and noise. And our goal is to estimate the vector, the signal f from n observations, y1 to yn, while the group elements are unknown and treated as random variables. So let's see two examples of this model. So the first example is the 1D MRA case. So here we have a 1D signal acted upon by circular shift. So in the left column, you see the problem. Here in this column with no noise. So basically, these are three different shifts of the signal, and each observation here is a solution, trivially because the solution is defined up to a group action, up to a shift. In the middle column here, you see the problem in the high scenario regime, where basically the signal dominates the noise. And here you can imagine it should be quite easy to try to estimate the relative shift, align the observations, and average out the noise. In the right column, you see the problem in the noise scenario, which is going to be the focus of this talk. And here, it seems very more challenging to estimate the relative shift. And the question is whether we can still estimate the signal in this regime, although it's difficult to estimate the shift. So this is the first example. The second example arises from technology called singular particle cryo-electron microscopy, or cryo-EM for short, which is a technology to reconstruct the molecular structures of biological molecules such as proteins and viruses. So in this technology, we take many copies of the molecule of interest of the protein. We freeze them in a thin layer of ice. And we take the ice with the embedded molecules, put it in the microscope. The microscope transmits electron from one side of the ice, and we get a tomographic projection on the other side. So these are the observations, P1, P2, and so on. And we can think about each observation as my 3D structure phi after a random 3D rotation, which the random rotation corresponds to the unknown orientation of the molecule in the ice, and a tomographic projection, and noise. And the goal is to estimate the 3D structure phi from n observations, P1 to Pn, while the 3D rotations are unknown. So you can see that this is not precisely a multi-reference alignment model because of tomographic projection, which is not a group action. However, from the perspective that I'm going to take in this specific talk, we can treat it as a multi-reference alignment model, and I explain it later on. In addition, the SNR in cryo-EM data is very, very low. So here you can see 4 experimental images. Okay, so again, we're going to focus on this very, very low SNR regime in our analysis. So I'm not going to talk too much about cryo-EM, but it's a technology that becomes very popular in recent years because it offers unique biological insights, unique insights into the biology of the proteins and viruses. And a couple of years ago, we wrote a survey about the different mathematical and computational challenges in cryo-EM. So these are the two examples that I'm going to focus on, the 1D case and cryo-EM, but our results are very general, and they hold for any compact group acting on a finite dimensional space. And there are many instances that were studied in the literature, And specifically, one very interesting result is related to the crystallographic phase retrieval problem, which is the computational problem in X-ray crystallography, which is again a very important application in structural biology. So when we think about MRA, we usually divide the analysis into two different regimes, the highest NR versus the lowest NR regime. So again, we want to estimate a vector F from n observations, where in each observation, the vector is acted upon by a random group element and we have some noise. And the first insight is that if the G's, if the group actions were known, if the shifts or the rotations were known, then the problem would be very easy. We can undo the group action, like to align the observation, and then just to average the observations. This motivates a reduction of this problem to the problem of estimating the group elements from the observation. For example, using group synchronization, if possible. However, if the SNR is low, which is again the focus of this talk, it's impossible. It's actually impossible to estimate the group elements. And when I talk about low SNR, I mean that the noise level goes to infinity. Just as an example, I took this figure from a previous paper, actually a paper with Will. The technical details are not very important here. What's important to note is that the y-axis here is the error, the x-axis is the noise level. And we see that when the SNR is high, the noise is low, the slope of the curve is around 1, meaning that the error behaves like the standard deviation of the noise, which is what we used to see in many signal processing applications. In the lowest SNR regime, the slope is completely different, and we see a slope of 3. So it seems like there are two different behaviors in the highest SNR and the lowest SNR regime. And now we understand this phenomenon, these different regimes. So in the lowest SNR regime, and the lowest SNR, I mean again that sigma, the standard deviation of the noise, and the observations, number of observations both go together to infinity. It's challenging and actually impossible to estimate the group elements. However, this is perhaps a bit surprising. We can still estimate the signal in this regime, even if we cannot estimate the group elements. So for example, in the 1D case, sometimes we can estimate the signal, although we cannot estimate the shift. And in cryo-EM, we can estimate the 3D structure, although we cannot estimate the rotations. And more than that, we can characterize the sample complexity of the problem with the optimized estimation rate. So if we denote by D the lowest degree moment that determines the signal uniquely, then n, the number of observations, should be much greater than sigma to the power of 2D. And this is a necessary condition for recovery. So for example, if D is equal to 3, as in many cases, then n should be much greater than sigma to the 6. And again, that's a necessary condition for recovery. And this is a nice problem, I think, because it takes this information theoretic problem and reduces it to an algebraic problem. Okay, so we need to understand what is the lowest order moment that determines the signal. Right? And it may depend on the vector space, on the group, on the distribution over the group, and so on. And in this line, I'm summarizing many papers, but generically, for many applications, for many different setups, D is equal to 3, meaning that we need to use the third moment, and therefore, a necessary condition for recovery is that n is much greater than sigma to the 6. And today, we're going to explore what happens with the second moment. Okay, when or how we can recover signal from the second moment. This implies that we need only sigma to the 4 observations, fewer observations than what we generically need. Okay, so that was the introduction and the motivation for this talk. And we're going to focus on the second moment of the MRA model. Questions? Again, we are very few people, so just feel free to stop me at any moment. Okay, so now we're going to start with the theoretical analysis. So each MRA observation, as I said, is drawn from this model. So we want to estimate F, and in each observation, F is acted upon by a random group element G plus noise. And we're going to assume the distribution over G is uniform, the distribution of the group elements. we study the second moment, which is the expectation of YY transpose, which is this integral, and it can be approximated from the data using the empirical second moment. And we know by the law of large numbers that if n is much larger than sigma to the 4, that almost surely the empirical and the population second moments are equal. So that's what we're going to assume, that we have exactly the second moment of the data. And if we're going to identify a class of signals that can be recovered from the second moment, this will imply, by the result that I showed you 2 slides ago, that the sample complexity for this specific class of signal is only sigma to the 4 and not sigma to the 6. So that's what we try to do. And we're going to start by first of all characterizing the structure or the algebraic structure of the second moment, and then we see how we can resolve these ambiguities. So we need 2 notions for the analysis. The first is the notion of group representation. And we follow standard terminology and we refer to the vector space V equipped with the action of the group G as the representation of G. For example, we're going to use to see 2 examples. So one is the 1DM array. In this case, V is going to be Cn and the group is Vn. And in cryo-EM, V is going to be the R2 functions over R3, and G is SO3, the group of 3D rotations. And a well-known result states that that any representation of a compact group is unitary. And this means that the elements of G act on V by unitary transformations or by unitary matrices. The second notion that we need is irreducible representation. And we say that the representation is irreducible. That's the definition if it has non-zero proper G invariant subspaces. Perhaps in other words, a representation is reducible if it's equivalent to the direct sum of other representation, and we know that any finite dimensional representation of a compact group decomposes into a direct sum of irreducible representations. So in a sense, the irreducible representations are the building block of the representation of the vector space that we are going to work with. Okay, so now we can start with the analysis of the second moment, and we're going to do it in 3 stages. In the first stage, we are going to work with a single irreducible representation. So V is some irreducible representation, and we're going to see in a minute that the second moment gives very little information about a vector F in V. So the key is noting for 2 things. First of all, the second moment is invariant under the action of G on V. So this means that F and GF they provide the same second moment, and this is true because the second moment, to compute the second moment, we just integrate over the group. And the second insight here is that we are going to treat the second moment as a linear transformation. So it's a G, more precisely, it's a G invariant linear transformation from V to V. And since V is irreducible by assumption, then Schur's lemma implies that it has to be a scalar multiple of the identity. Okay, so this provides us the first result. So if V is an n-dimensional irreducible representation of a compact group G, and we identify V with Cn with via a choice of some orthonormal basis, then the map, the second moment map from Cn to Cn squared is just the map between F and the norm of F, the norm squared of F times identity. So that's all the information that we get from the second moment for an irreducible representation. So that's the first stage. The second stage, now instead of considering an irreducible representation, we're going to consider representation V, which is a direct sum of R copies of some irreducible representation V0. So V is a direct sum of R times V0. This means that if we take a vector F in V, we can write it uniquely as this sum of F1 to FR, where FR is in the Rth copy of V0. And this model, it may seem a bit strange for most people, but probably you understand it. But it is motivated by cryo-EM, where instead we need to think about, instead of thinking about R3, we think about R3 as a collection of concentric spherical shells. Okay, so like it's a shell, like many shells, and therefore the action of SO3 will be that actually we're going, SO3 is going to act on the space of L2 functions over the sphere S2 multiple times, like with different copies of that. So it's a discretization, some kind of discretization of R3 that's going to be very convenient for us. Okay, so if you view an element F as an R tuple F1 to Fr, each one of them is an element of V0, then by the same consideration as before, the second moment determines all the pairwise inner products. So we get this inner product between Fi and Fj. So that's information that we get from the second moment for this model. And if we think about F as a matrix, A, matrix of size n0 times R, where F1 is the first column, F2 is the second column, and so on, then we can think about the second moment just as an R times R emission matrix A star A. Okay, so we want A, which is equivalent to F, but we get A star A. So this means that the second moment provides us F, the vector of interest or the signal of interest, up to the action of a unitary group of dimension n0, where n0 is the dimension of the irreducible representation V0. Okay, so that's the information that we get from the second moment in this case. Now we're in the third stage of the analysis, the most general case. So here we consider a general finite dimensional representation of a compact group, and it takes this form. So the representation V is the sum, direct sum of k distinct irreducible representations, and each one of them may have Rk copies. Okay, so that's the general structure of a finite dimensional representation. So this means that if we take any signal or vector in V, we can write it as follows, where we sum over the different irreducible representations and over the different copies, and Fki is in the ith copy of the irreducible representation Vk. Now again, we think about the second moment as a G-invariant linear transformation, generally, for example, from V1 to V2. And again, we know from Schur's lemma that the irreducible representation, each one of these terms, the second moment, has to be either zero or an isomorphism. Again, this is just Schur's lemma. And this implies that since Vn and Vk are non-isomorphic by assumption, then there are non-zero G-invariant linear transformations. So the second moment has to be zero, basically. That's what Schur's lemma tells us. And therefore, the second moment determines this inner product. So this inner product between Fki and Fkj for all ij goes from 1 to R, but decay is the same. So there are no cost terms between the different irreducible representations. And again, if we just think about Fk as a matrix, we call it AK, where the columns are the Fk1, Fk2, and so on, then the second moment gives us AK star AK for K goes from 1 to capital K. So that's the information that we get from the second moment. So this leads us to the following theorem. So if V is of this structure, and then the vector V is determined from the second moment up to this ambiguity group, which is just the product of K unitary matrices with the corresponding dimension. Okay, so that's the group of that's the ambiguity group when we compute the second moment. Is that clear? Okay. Okay. So let's see two examples. The first example is trivial, and the second is less trivial, but at least for Will, it will be very familiar, I think. So the first example is for one DM array. So now we have a group G G, the group G is Dn acting on Cn by cyclic shift.
Actually, Tamir, do you mind going back to the previous slide? I want to make sure I'm following what it's.
Yeah.
So the theorem. Well, let me see. So the ambiguity group is the group. I mean that's the intrinsic group to the problem, or it's equivalent to that. I mean, there are not more ambiguities than are intrinsic to.
What do you mean by intrinsic here?
Well, I mean, so maybe you're going to talk about these examples next, but say in the cyclic case, that there's an intrinsic ambiguity, right? You can't recover a vector up to, you can only recover a vector up to translation. That
yeah, but it's here. It's within this. It's a subgroup of this group of ambiguities. But this ambiguity of group is much larger in this intrinsic ambiguity that you are referring to.
So that was exactly my question. So it's that this there are more ambiguities here that guarantee.
Generally, much more. There are much more ambiguities. Yes, but you're going to see it in the next examples. I think it's going to clarify it.
Okay. Thanks.
Okay. So the first example is this 1D case, and so we have the group G acting on Cn, and we know that in Fourier domain, or that is, I know, basic. I'm trained in actual engineering, so this is like a basic signal processing fact that you know from school. That basically the cyclic shift in Fourier domain is like multiplication by roots of unity. So, for example, if omega is the roots of unity and f is a vector in Fourier domain, then the action of omega is just this action. And the vector space Cn with this action it decomposes as a sum of one-dimensional irreducible representations, V0 to Vn to Vn minus 1. So we have only a single copy, R is equal to 1, and each one of them is of dimension 1. These are basically the complex exponentials in Fourier analysis. And the results that we derived in the previous slide basically tells us that the second moment of a vector f in Cn in Fourier domain is just the power spectrum. So you just get the absolute value squared of the Fourier coefficients, which is not surprising, but it's also we also derived from our general results. And it means that the second moment determines the vector f up to n times u1. U1 is just the group of unitary matrices of dimension 1. These are just the complex exponentials. So in signal processing terms, we say that we got the Fourier magnitudes, but we're missing, or the ambiguity group is the so-called Fourier phases, right? And this is exactly this problem of recovering a signal from the power spectrum where we don't know the Fourier phases. It's called the phase retrieval problem, which is an extremely important problem in optical imaging and crystallography and in some other engineering applications. So it's a very important problem. This problem is very important. So this is the first example. It's quite simple. The second example is a bit more involved, but again, Will, I'm quite sure that you are familiar with this problem. So now we want to think about cryo-EM. So the space is the space of Irreducible function on R3, but we're going to discretize it. We cannot work with this space directly, and we're going to discretize, as I said before, as R concentric shells. So the representation is going to be of this form V. It's going to be sum of Vk with R copies, where the R copies are the different shells, and K is usually referred to as the band limit. Again, like in Fourier Fourier analysis, and Vk, and now with written K, is the 2K plus 1 dimensional irreducible representation of SO3, which corresponds to harmonic polynomials of frequency. It should be K, or frequency K. And we know that an orthonormal basis for Vk is the set of spherical harmonics, okay, which are indexed by K and M. So now we think about an element F. Again, in cryo-EM, an element F is a 3D structure, a molecular structure. We think about it as an R tuple, F1 to Fr, which Fr is in the space of Irreducible function on S2 on the sphere. This should be K band limited function. And we can write each Fr as this sum over the spherical harmonics where the AKM are the so-called spherical harmonic coefficients. So basically, recovering F is equivalent to recovering the unknown coefficient AKMR. So that's what we actually want to determine in cryo-EM. Now there is something which is a bit unique, and it's not obvious, but it can be shown that in cryo-EM we have the tomographic projection, but tomographic projection we don't lose information because of the tomographic projection when we compute the second moment. This is obviously not generally true. In cryo-EM, of course, we lose information because of the tomographic projection, but specific for the second moment, we don't lose information. And therefore, we can think of cryo-EM as an MRA model where the group is SO3. Okay, this is true only when we think about the second moment. This is, again, it's not true in general.
Wait, sorry,
And,
just a question about that.
Yeah.
So I'm not quite sure what that means exactly. So are you saying that the second moment of the projected images is somehow you can recover the second moment of the 3D volumes from the second moment of the projected images?
Yeah, so if you think about, suppose you have like a vector that represents the second moment of the unprojected cryo-EM model, and a vector that corresponds to the projected cryo-EM model. So there is an invertible correspondence between them.
I see.
It's a bit surprising, but it's true.
Okay, I believe it.
Well, yeah, thank you. It's not obvious, and it's true only for the second moment. This is not a general statement about cryo-EM or something like this. It's true for the second moment specifically.
And how, is that true in other, like in say a 1D MRA case? If you were to do 1D, translate a signal and project, there would not be.
I think you can actually try to think about what type of models, for what type of models that this kind of statement is correct, but this is not generally true.
I see.
It's actually it's very difficult to say exactly what does it mean to do the equivalent of tomographic projection in the 1D case. It's like we don't really know, I think, to characterize what's the right equivalent of that.
Well, how about if you have a 2D image and you project it onto a 1D, onto a line?
Yeah, right, but this is very different because in the 3D we have, there is a huge difference between the 2D case projected to 1D and the 3D projected to 2D. And let me think for 1 second. From 2D to 1D, it's definitely not true. It's probably true for higher dimensions, like if you think about like 4D image projecting to 3D or something like this, but I'm not completely sure.
Okay, that'll be useful for studying, 4D molecules.
Yeah, exactly. Yeah,
okay.
this kind of structures.
Yeah, that was a joke, by the way. Okay.
In hidden dimensions. No, but so I think we can probably think about on what type of model this is correct, but this is not generally correct. Let's put it like this. And this is also not true for example, if you want to work with a third moment. So you definitely lose information because of the projection when you compute the third moment.
Okay.
It's true for the second moment, only for the second one. Okay, so now we can invoke directly the results that we have seen before. So if we let AK to be the matrix with the coefficient AKM R, so the second moment determines these matrices AK star AK, where AK goes from 0 to K or from 1 to K, depends how you count. Okay, so this is direct corollary of the algebraic structure that we derived before for any MRA model. And this is because we can treat cryo-EM as an MRA model when we think about the second moment. And this implies that the second moment cryo-EM determines the coefficients or the structure up to a set of K unitary matrices. And the ambiguity group is this ambiguity group of K or K plus 1 unitary matrices of dimension 2K plus 1. Now, something that we'll know for sure that this result is not new. It was actually derived with Zvi more than 40 years ago from Weizmann Institute. But I think that in some sense, everything I showed you so far can be thought of just as a generalization and abstraction of the result of COM that derive this result very specifically for the case of cryo-EM. So these are the so this is the algebraic structure of the second moment, and I showed you two examples. And now I want to think about ways to resolve the ambiguities, like what kind of, like when we can resolve the ambiguities and recover these unitary, unknown unitary matrices. And to this end, we're going to use sparsity. And just to motivate sparsity, I took four molecular structures and I just computed their wavelet coefficients and I showed the distribution. I just showed the distribution of the wavelet coefficients. And here the important part is to know that basically the coefficients decay very rapidly. Okay, so this means that we can at least approximate the structure quite well with few coefficients. Okay, this motivates us to think about sparsity. So the result that we derived for sparsity, so when we think about sparsity from the mathematical perspective, this is generally a problem in algebraic geometry, and my collaborator Dan Edidin is an expert in this field. Basically, you want to check. We have this orbit of different possibilities from the second moment. We know that we get the structure up to a set of unitary matrices, so this is an orbit, and we ask the question when this orbit contains at most one k-sparse signal. Okay, so that's exactly what people in algebraic geometry know to solve. So this is the result. So we have a representation of this form, the general structure. The total dimension of the representation is n. We call it n, and m is this sum over this thing. And the result states that if our vector signal is k-sparse, where k is more than n minus m, then it is uniquely determined by the second moment up to a global phase. Okay, so up to a global phase, it resolves the missing orthogonal matrices. So I also need to say that this result is not necessarily very, very tight. It's not necessarily the best result that can be derived, but at least if you have enough copies, if R is large enough, then it seems quite tight. So for example, if we apply this result to cryo-EM, and the number of shells or enough copies is greater than 2L+1, then K should be smaller, more or less, smaller than n/3. So it means that if the structure can be represented in some generic basis where the number of non-zero coefficients is at most 1/3, then it can be recovered from the second moment. And this implies that the sample complexity for such structures is only sigma to the 4 and not sigma to the 6. There is another paper that we derived an analog result. This is a paper with Yuhao, Joe, Oscar, and Amit Zinger, where we showed that also for a sparse mixture of Gaussians, we can also recover a sparse mixture of Gaussians from the second moment. So also for this type of structures, sigma to the 4 observations is enough. And again, we have analog results for different cases, among them the case of X-ray crystallography, which is again a very important application.
Wait, so sorry, I want to just clarify this statement of the theorem. So the statement is for a generic choice of orthonormal basis, a generic k-sparse function, blah, blah, blah.
Yep.
Okay.
Yep.
But I mean, any signal is sparse. I mean, you could take a basis where the first basis element is the signal itself, right? Am I missing something? Like
yeah, but this is not necessarily, but this is not a generic basis.
But why not? I mean, if the signal, if you take, say, a random signal, or maybe not random, but you take a signal, you perturb it a little bit, it's not going to satisfy some polynomial equation, right? You can always add noise to it or modify it a little bit. So it
yeah,
seems, Do you see what I mean? Like
You're saying it's redundant. It's redundant to say both generic orthonormal basis and generic k-sparse function.
I mean,
That's
perhaps
what
the statement can just be that for a generic signal.
No. Actually, this is no. So the signal itself is sparse, right?
But
So
it's
you cannot
sparse
just
with respect to some basis, but it can be any basis as long as it doesn't, as long as you avoid the roots of some polynomial system, right? So as long as the signal itself avoids those roots, then you should be fine.
I agree in general, but I'm quite sure that we need both. Like, we don't really know how to quantify, like not to quantify, how to give like explicit conditions for these generic terms. So I don't think we can just remove any of them. I understand what you're saying, and it is definitely correct in general, but I don't think we can just remove any of them.
Oh, I see. When you say a generic k-sparse, you don't necessarily have control on the sparsity.
No, suppose the sparsity is fixed, it's k.
No, but I mean, you don't have control on which basis elements are selected, so something like that. So you couldn't.
Yeah, so in the proof itself, there are two stages, and basically you need generic for the first, generic orthonormal basis for the first, and then generic k-sparse for the second. I don't think they can just be removed. Like in practice, it has to be correct, but I don't think it can be just removed.
Okay.
Okay.
I believe.
Like basically, if you fix, the way I think about this, if you fix some bases, which might be generic, there might be like bad k-sparse signals within this fixed basis. So also in this basis, you need to choose like a generic, like you need to generic condition. So it's not going to be the bad ones.
I see.
Okay, something like this.
Okay.
So that was the algebraic structure, and now the next part of the talk, it's probably going to take me something like 5-10 minutes. This is more about the algorithmic part. It is based on a different work with, again, I said Joe and Yuhao and Oscar and Amit. And it's actually based on a simple insight, which I think it's quite nice. So to explain this idea, I want to discuss the problem of crystallographic phase retrieval. So that's the problem of recovering a sparse signal from a sparse spectrum. So that's the main computational problem in X-ray crystallography. And we can think about this problem as a problem finding a signal F in the intersection of two sets, A and B, where A is going to be the set of all signals with the same measured data, the same power spectrum, and B is going to be the set of sparse signals. I want to find a signal which has the correct or the measured power spectrum and is sparse. So it's quite simple to define projectors that can be computed efficiently into these sets. So for example, given some signal F, the projection onto A, TAF, basically takes the signal F, compute the Fourier transform, keep the Fourier phases, and combine it with the measured Fourier magnitudes. And therefore we get a signal with the correct or the measured power spectrum. So that's going to be this projection. The second projection is just a sparsity projection. So we just keep the largest K entries of F and zero the rest of them. So we have two projections into these sets. And now we can, I think the most natural thing to do is to do alternating projection. It's also called the Van Neumann's algorithm, where we take F and we apply PA, PB, PA, PB, PA, PB, and so on. So it makes sense to try, but in practice, it doesn't work very well, and it tends to stagnate very quickly at bad or irrelevant fixed point. But this problem is very important. These kind of algorithms are very important for the physicists in phase retrieval, for example, in crystallography. So they actually take these two projections and they designed algorithms that use these two projections in a more sophisticated way. So there is a family of different algorithms. I don't know which one is the best. I like the Renat reflector or RR. which is one of them, because it has this nice property that if there is no noise and the model is perfect, then basically it stops only when the two constraints are satisfied, like in the intersection of the two sets. There is no magic, so the running time might be very, it may take many iterations to converge, and it seems empirically actually that the running time is exponential in the sparsity level, but we don't really know how to analyze it theoretically. So the nice insight is that basically we can take these ideas that were developed for phase retrieval and generalize them to signal recovery from the second moment of any MRA model over compact groups. So we need two projections. So one projection is the sparsity. That's easy, that's the same. The second projection is the projection into the, again, it's like the projection of the data onto the set of all signals with the same measured data. So in our case, we know that the second moment determines the signal up to unitary matrix or a set of unitary matrix. So given some signal and given the measured data, the true signal up to a unitary matrix, we need to find the unitary matrix that minimizes the distance between the current signal and the orbit of possible signals. And this is a known problem in algebra. This is just the Procrates problem. And we know that we can solve it just by using SVD. So we can use the same ideas from the same algorithms that were developed for phase retrieval just for recovery of from the second moment of under the MRA model. And we apply this technique, and we specifically apply this algorithm. We apply to cryo-EM, where we assume sparsity in the wavelet domain. There is nothing special about wavelets. It's not necessarily the best thing to do. It's just quite natural and it's easy to do. So that's the reason we tried this basis. Perhaps there are better bases. And importantly for us, the algorithm, it requires only the second moment. So we need only sigma to the 4 observations and not sigma to the 6. So this is the results that we got. You see from left to right, here you see two proteins that I'm not completely sure how to pronounce their names, but these are two structures of two proteins. And this is just the shape model in phantom. This is in green. In purple, you see the same structures, but after smoothing, like after band limiting. So that's what we're actually trying to recover. And in blue, it's what we recovered using the R, which it seems, I think, quite good, especially since we use fewer observations, we think, than what people use today in cryo-EM. So that's the numerical result that we got. And this is my last slide to summarize. So we've shown that in this talk, I try to convince you that sparsity can be used to improve the sample complexity. And currently, we are trying to think about different priors to improve the sample complexity. For example, now generative models became very popular. So we're trying to see whether we can, for example, under a prior of generative model, we can still improve, we can get an improved sample complexity. From the algorithmic part, we generalized this family of projection-based or phase retrieval algorithms to MRA models, including cryo-EM, and now the question is whether we can integrate sparsity into more practical scenarios. So for example, we assume that this distribution over SO3 is uniform, whereas in practice, it's non-uniform. So the question is whether we can extend it or to account for the non-uniform distribution. And the last part, which I think is extremely interesting, is the question of computational versus statistics. Like even if we can show that some class of signals, for example, sparse signals, can be recovered from sigma to the 4 observations, it doesn't guarantee that we can actually design an efficient algorithm that will recover at this estimation rate. And the question is whether there are some computational statistical gaps that you need to pay for statistical efficiency, you need to pay in computational time. So this is something that we're not sure, but that's something that we are trying to understand nowadays. And that's it. Less than 50 minutes. Thank you.
Thank you. It was a great talk. Very, very interesting. Yeah, we do have time for questions. Until people are ready to ask questions. I'm curious, so you mentioned the the generative prior instead of a sparsity prior. Did you? I didn't get it. Did you already have some numerical experiments for this, or it's completely open?
No, it's completely open, but basically, when I think about generative models, at least from the theoretical the theoretical aspect, you can think about just that there is some low-dimensional, I don't know, ambient space or some low-dimensional signal vector that goes through, for example, I don't know, matrix multiplication plus some nonlinearity. For example, this is like a one-dimensional neural network. And under this model, if you assume that the signal itself lies in some lower dimensional space, you can imagine that somehow it's similar to sparsity, because there are less parameters that control the structure. It actually maybe simpler to analyze than sparsity. So the question is whether we can show that. I don't know. And if, for example, we can come up with this kind of very simple one layer of neural network, can we do it for 2 or 3 or 4, and so on, to understand the dynamics between the dynamics, I mean, like the relation between the generative model and the sample complexity. So we didn't do it yet, so I don't know if it's true, but people did it for related problems. For example, phase retrieval, not for the actual phase retrieval, but for this random phase retrieval setup, people actually did this kind of analysis, and I think we can also do that. Like, but again, we didn't. So we need to see. Maybe next year, I can explain about that.
Yeah. Okay. Thank you.
But actually, I have a question on your second bullet point. So when the distribution over SO3 is non-uniform, isn't it known already that the second moment is sufficient generically?
Not precisely. They know that there are finite list of solutions from the theoretical part.
Yeah, they have a weak result.
But perhaps more importantly, the numerical results are quite weak. If you look at this specific paper, the numerical results are quite weak, and we are hoping that, for example, using sparsity, and perhaps we need to use most stronger priors than that, you can improve the results dramatically.
I see.
I think basically that's more generally, you are familiar with that. If you want actually to in practice to apply the method of moments to cryo-EM at some point, either in this scenario, what we worked on of recovery from directly from the micrograph and so on, then we need to we need to be able to apply very strong priors on the structures. It might be either sparsity or generative models, or I don't know, but I think that's the key. Like from the more cryo-EM perspective, I think that's what we're missing.
Yeah, that makes a lot of sense.
Yeah, but again, I don't know exactly what this prior should be. So currently, I'm just talking about that.
Do you have empirical justification for sparsity in a wavelet basis? Like if you take a 3D volume, like an actual one, and expand it?
Yeah, so we did that.
Did you show that slide?
Yeah. So that's actually.
All right. Yeah, there you go.
Yeah, but it makes a lot of sense, right? We know that almost if you take like almost any image and just expand it whether it is going to be approximately sparse. This is not very surprising. And there are some other works that use wavelets in cryo-EM, but no one actually pursued this direction too much. And again, it's not clear that wavelet is the best way to go. Like it's just quite natural and easy to implement for us. But you can imagine that there are better bases out there that we just need to find, or perhaps to learn from current structures and so on. So whether it's just on one hand it's rich enough, on the other hand it's easy to use, that it makes sense to use it for us. But it's not necessarily the best.
Yeah, I mean, it makes sense because they're kind of, well, it depends on the basis. I mean, it depends on the choice of wavelet, but the local behavior can vary
Yeah, so
dramatically.
So this is how the Howard wavelet, like the simplest one.
Right.
So I didn't.
But you also said you had some results. You kind of went through it quickly on Gaussian mixtures.
Yeah. So that's a different paper. Yeah.
So I mean that Gaussian mixture model. I know that's I know in cryo they sometimes use these kind of atomic models, right? Where basically you put a very concentrated Gaussian at different points. I mean, perhaps you can construct the basis of difference of Gaussians or something to sort of take Gaussians and orthogonalize them, and that might be sort of if that model is correct, then you might be able to prove sparsity with respect to a basis like that.
Yeah, the problem here is that, again, I didn't just, the setup is very different, and I didn't put the details here because we need a complete introduction. But basically, the weak point of this work is that basically we consider a continuum. So basically, you assume that you're going to assume that the centers of the Gaussians are just they somehow in R3, and they need to satisfy some very weak conditions. But once you start to discretize it, it's not completely clear how the results may change. So it's hard to compare between the two results because the setup itself mathematically is quite different. So we need to be a bit careful here. But it's also a nice result. It's a nice paper. This is with Amit's group, and so.
Yeah, I see a lot of names I know on that paper.
Yeah.
So I see a lot of names I know throughout the whole talk, but that's it.
Yeah. Yeah, it's a small world, right?
Yeah.
And that's it.
Yeah, it's very nice. Does anybody from the audience have any questions? I feel I've been monopolizing the question. That's
It's you and Gilad, right?
So that there are a bunch of other attendees, or well, a few have left because we're nearing the end. But
Yeah.
now 8 others.
I didn't see it, so I didn't actually.
You only see the co-host, but you don't see the other participants.
Oh.
Some of them
Okay.
already left, but there are several that are still here. So there were about 20 people.
I felt like I'm talking only to you and Will, which is also okay. Like, so like anyone else?
Yeah. So if anyone has a question, you can type it in question answer box or raise your hand. Okay. So yeah, but some people are leaving because they have classes. So yeah, thank you very much. It was a great talk. I appreciate it.
Thank you very much, and thanks for the invitation, and it was nice. Thank you.